Welcome, everyone. Thank you so much for joining us here. It's third day of Next, and I hope that you've had an invigorating and enlightening time here. Thank you so much for coming and joining us today for this session about bringing the power of machine learning to your streaming data. One of the things that I've said as a product leader over the last 15 years is that speed is always a feature. No organization wants to have to endure batch jobs or outdated information. We want to make the best business decisions in real time for better customer experiences, for increased revenue, better margins, happier employees, and more satisfied customers. Hi, I'm Sachin Agarwal. I'm a group product manager here at Google Cloud. I'll be joined by my friend Wei, who's a developer advocate who will be doing a demo, and then of course Edgar, our hero from Spotify, talking about how they use Dataflow and Dataflow machine learning at Spotify. I think everyone here is familiar with the fact that data is our competitive advantage. And technology now allows us to take advantage of that data in real time with the power of stream processing and real-time activation. Dataflow is amazing. It powers streaming intelligence for modern digital requirements from the very simple to the most extremely complex use cases. Google, we're proud to say, invented modern stream data processing with the Dataflow paper and the Dataflow service. And we've continued to build on that momentum since the invention of Dataflow back in 2016. So it's not just the OG, but it's the very best solution for streaming and batch data processing. Dataflow is highly automated, fully orchestrated, ultra simplified, and widely efficient. Recent Dataflow innovations include all of the work around machine learning, improvements in our serverless platform, investments in the open source SDK Apache Beam, and richer tooling for better control and understanding of your Dataflow pipelines. Today's session focuses on that first one, machine learning. We'll hear more from Edgar in just a little bit, but I wanted to ground with the use case for today's discussion. Here, Spotify is using machine learning and Dataflow for audio files. You can see the massive benefit of going from batch to stream processing. The latency goes down from almost 2 hours to just a matter of minutes. And in this case, there are multiple machine learning models being used in a single DAG, in a single Dataflow pipeline. So it's just one good use case, but there's so much to Dataflow for machine learning. Dataflow ML has a very rich feature set: inference, data preparation, GPU support, and more. There's so many things you can do with Dataflow from. And note the integrations are not only with Google Cloud sources and sinks, but also with other third-party or open source sources and sinks. You can use Vertex AI, and we'll talk a little bit about that, but also other machine learning frameworks. And there are partners like Hugging Face and TensorHub that you can use Dataflow with as well. It's incredibly powerful, and one of the things that we've tried to do, and we'll talk about in today's session, is bringing that power to everyone through simplicity and innovation. So let's take a little bit of a step back and cover the basics of how Dataflow works. Dataflow is an execution engine for Apache Beam pipelines. Apache Beam is an open source SDK for large-scale batch and stream unified data processing. Beam is where you define your pipelines, and Dataflow is an execution engine, a runner for running those Beam pipelines. Because Beam is open source and portable, you can run your Beam code anywhere you want to, on premises, on the edge, on other clouds. But of course, we think Dataflow is an excellent solution for that. Let's talk a little bit about the basic Beam building blocks, and you'll see how it all comes together for these machine learning use cases. So we start off with P collections. P in all of these stands for parallel, because when we're talking about parallel processing, that's really where Beam and Dataflow shines. So P collections are just groups of data or groups of information, and the elements, as I said, are stored in parallel. And then what you want to do with that collection of data is you want to do some processing on it. And so you need to transform these elements, and that's where P-transforms come in. Essentially, at a very, very high level, P transforms turnkey collections into other P collections. So we describe this action with a DAG, with a pipeline. And all it does is it tells how do these P collections work together and what are the transforms that we're doing to do some processing on that set of data. So we've got a very simple example where we want to read files from our physical stores and files from our online store. The pipe operator in this code just means apply the action. So what we hear is we want to bring together information from our table that has the information about our online store and the information from the separate table that has information for our in-person stores. Okay? So to do that, we're just going to use a very simple flatten operation. And it brings that together, and you can kind of just visualize this map of how this is working together in the DAG. And then we want to do some analytics. Let's say we want to see what are the top 10 selling objects across everything. So we're just going to do a very simple count using the combiners, and we're talking about per key. In this case, you can see 10 is the key, so we're doing the top 10 selling objects. All right, now we know what that is. We want to activate it, so we're going to write it to BigQuery for further analytics and downstream activation. OK, so that was a batch pipeline. But what if we want to do streaming? So all we need to do is add the window primitive. Windows slice the P collections up, usually by timestamps, but can also be custom defined based on the elements of the data itself. So it's really flexible for a wide range of data processing and machine learning operations. So with the window primitive, I've changed it from flat files to a pub/sub streaming source within a fixed windows. And you can see there's 1,000 milliseconds. So every second, we're going to go through and do these windows. So it's a 1-second window that we have here. And then we're just writing back to BigQuery for that sales. So it's very unified inside Apache Beam, where you can go from batch to streaming and back by just adding the windows in there. So we have a use case here where we're talking about analytics, top 10, put into BigQuery, all the rest of it. But what if you wanted to use a machine learning model for your business logic? What if you wanted to use that ML model to do some really cool or difficult processing? Well, you can do that with Beam as well. You absolutely can use those same Beam primitives that I talked about for your machine learning models. But it turns out going from a toy or going from a demo to production is a lot of work. There are all sorts of edge cases and things that you'll need to be able to handle. So we've worked with the Apache Beam open source community to add the idea of turnkey transforms. Turnkey transforms are higher level processing objects for a specific use case. Again, this is building on those low-level building blocks that have been proven at scale, so they're a rock-solid foundation for these new turnkey transforms. So given how important it is for organizations to take advantage of machine learning, we wanted to make that the first use case for these turnkey transforms. So, organizations that may not have data engineering talent and in-house, we still want to bring that power to them. So you don't have to reason about this, from first principles. So the very first turnkey transforms that we added are run inference and ML transform. So run inference does both streaming and batch machine learning inference. And ML transform is a dedicated turnkey transform for specific pre-processing things that we do for ML model training or inference. And we'll talk a little bit about both of these. So if you were going to do this with the standard Beam primitives, you'll see some of those do funds and group by keys on the right. You can. You absolutely can. But what we've done with run inference is we made it so much easier. You have easier sharing of the model, error handling and deadloaded queues built in, observability, all of that encapsulation and pre and post processing. And for streaming ML, you can update the model on the fly. Super, super cool. So with run inference, it's a single line of code that the user needs to write. And then we complicate it from there. So run inference supports a wide range of machine learning frameworks, not just TensorFlow that comes from Google, but also things like PyTorch, XGBoost, scikit-learn, and so on and so forth. But you can also use your own custom model handling framework with this simple interface. So many of our largest Dataflow ML customers actually use custom model handlers with run inference. And that provides a lot of flexibility and power when you have these very, very niche or very, very fine-trained models. So there are specific features, as I mentioned, for pre and post-processing of data in a P collection, again, making it easier to run these inference objects. And then we had some specific support for exception handling. And so what the failure states does is that it writes to a P collection. all in one place for all of your failures, but it lets all the successes continue to run for the rest of your pipeline. So it doesn't block you when you have these exceptions. We put it all in one nice place so you can figure out what to do and then work on your pipeline or modify it as you need to. Now, what you can do is you put a model in its entirety into that pipeline up to the worker memory limits. So you can have an entire Gemma model, and you'll see Wei will have that in his demo. But there are thousands of models out there, right? And they're shared via various model repositories. So run inference, we did the work to allow you to pull from them automatically. So you can pull down the open source model that you want from either TensorHub or from Google Partner Hugging Face. And because complex use cases may require the use of more than one model in a single pipeline, there's a p-transform that you can use to route the right data to the right model. So it's kind of like creating your own mixture of experts in the Dataflow pipeline itself. Incredibly powerful stuff. And as I said, that streaming model update is super awesome because you can have this long-running, continuously processing, streaming ML pipeline, but your other team, who's working on fine-tuning or training the model may have a model update, and you can hot swap it in without having to restart that pipeline. So you end up with better business experiences continuously because of the power of Dataflow and the way that we do streaming and batch machine learning. And of course, I mentioned before, Vertex AI, another great Google product, deep integration there. So you can do online serving continuously as well as batch prediction. The ability to use any of your custom models that you're managing inside Vertex AI, and then you can actually call the model remotely if you're using the Vertex AI model handler. You don't necessarily have to put the model itself in the pipeline if you don't want to. And of course, because it's a Google product, that deep monitoring and tooling from this integration, all of it's in there that provides full visibility and control that you need. So a lot of the things that I mentioned before actually are improvements and enhancements to the Apache Beam SDK. But of course, we've made attendant improvements in Dataflow, the service as well. So here's an example of something that we've done to take advantage of run inference in the Beam model on the Dataflow service. So you have an example where an organization may have lots of large models, and they only have a single model in memory. So Beam, by default, will spin up multiple processes per worker machine for efficiency. So here we've added that model handler in the middle, which manages the memory for you. All you have to do is say large model equals true in your model handlers. What that happens, or what that allows, it allows the model to sit in a single process that the other processes that you see around here in the red talk to. And because high throughput inference may require different architectures than standard large data processing, large value data processing type, this improvement in Dataflow specifically for machine learning workloads makes it easier for organizations to profitably take advantage of the power of machine learning without wasted spend or running the pipeline hot. So this is an example pipeline. We actually have 6 different models, right? In this case, you have a voice prompt doing a bunch of stuff and returning a response. And so if you had to hand code this DAG with 6 different models and all of that with the Beam primitives, you absolutely could do that. But it would take forever and a month to validate. With run inference, you just do that for each of these 6 steps, and you can make that pipeline in just an hour. Again, what this does is it's democratizing streaming and democratizing the power of machine learning for as many organizations as possible. We're really, really proud of the technical innovation that we do, but the ergonomics that we invest in as Google across both open source Apache Beam and Dataflow as a service to make it as easy and accessible to as many people and organizations as possible. So, run inference was the first one, super successful, and so we added a second turnkey transform called ML Transform. And this is all about pre-processing your data specifically for machine learning use cases, making sure that data is tip-top. Great for that, right? I think we're all familiar with the garbage in, garbage out problem when it comes to machine learning, and ML Transform solves the garbage in problem. So there are common things that people do to prepare their data for machine learning use cases. A very common one is actually creating a vocabulary. So here we've got compute and apply vocabulary, which actually takes TensorFlow extended code, and based off the words that exist in the P collection, creates a dictionary. So what you're doing is you want to use the same vocabulary with the same model across your organization, because otherwise things get mixed up and you don't end up with the right results. And so what this does is it kind of hermetically seals this vocabulary that any pipeline in your organization can use, and using that same model. So that way it allows you to scale out your ML team and your processing team, and allows people to reshare that code and reshare these vocabs. That, again, accelerates the ability to drive business value through the power of Dataflow. Another thing you can do, obviously, is generating text embeddings for your model training. Here, we're calling the Vertex AI text embeddings API at the very beginning. And then again, one of the things I talked about is when we're using Vertex, you can actually pull models from other places. So here, we're pulling the model from Hugging Face. And you just do that where the embedding transform is and where you're pulling it from. So you see the text embedding model name, that's where you can put in the remote call and say, this is the URI for what we need to do. So this is just the beginning for ML Transform. There are lots of different specific pre-processing use cases needed for machine learning, and we're really excited to continue to invest here. One of the other things that we're doing with simplicity is making IOs in Apache Beam even easier to use with Dataflow. So Iceberg is a new IO that we have. It's, for most folks know, Iceberg is the most well-supported data lake format, fully supported by Big Lake, BigQuery, and lots of other organizations. And this now makes it super easy to land your data in Iceberg format from any of the 40 sources that Apache Beam supports. And again, it's really similar to run inference because we've made this support inside Apache Beam, but then in the Dataflow service, Dataflow will manage this IO for you and will automatically use the latest version of the IO connector, and in the near future, automatically do pipeline performance optimizations based on the running metrics of your pipeline. Again, higher throughput, less wasted spend. Another thing that we've done, and this is an announcement that actually came out literally today, is we've made it easier to write Dataflow pipelines with a new YAML SDK. So now you can define a pipeline as a configuration defined in YAML instead of writing code in Java or Python or Golang. So it's very, very easy. And soon we'll actually have the ability to do this YAML building inside the Dataflow UI. Really, really excited again about democratizing access to the power of stream data processing in Dataflow. And last thing I want to talk about specifically around Dataflow ML is the deep GPU support. So any robust tool for machine learning needs deep GPU support, and you can use a wide variety of NVIDIA GPUs in your Dataflow workers, and more to come soon. But one of the things I want to highlight is more than just check the box, we've got GPU support, we've done something cool. So in this example, we've got 3 different pipelines. One that uses small VMs where we're doing something simple, one that's using GPUs for something heavyweight, and a third one when we need to scale up and down. So you could totally do this. This is a great way to make sure you're not wasting spend by having 3 separate pipelines. Because otherwise, you would have to take that beefy part and have a pipeline with those workers, and you're over-provisioning. Well, what did we do? We did something really cool. We did something called right fitting with the GPUs. So every stage of a single pipeline can use different workers. So for simple mapping, at the very top, we've got small VMs. For that enrichment, we've got the GPU boxes. And then at that last stage, we have a dynamic worker pool that scales up and down within the memory bounds. And so you can reason about your use case with a single pipeline without having to use multiple different pipelines just for efficiency purposes. This is really, really awesome because it allows both your incredibly intensive and your simple workloads to be in a single pipeline, making it much easier to test and reason about the jobs that you're doing. And with that, let me bring Wei up to the stage to give us a live demo of the capabilities of machine learning. Wei.
Thank you, Sachin. So let's take a look at a running demo right now. For those who are not familiar, this is a Dataflow job console, the job UI specifically. And this job has been running. I launched it a little earlier to save some time for everybody. Before I go into the code, I'm going to go through the pipeline really quickly. For those who are familiar, this should look like a regular Dataflow job, and it is. The nice thing is there is a run inference transform here. So as Sachin mentioned, each one of these green boxes is a transform. To begin, we read from two PubSub topics, topic A and B. Not very creative, but it works. And then we flatten it. So a flatten is akin to almost like a SQL union statement. We're merging the two pipelines together, and then we perform inference. That's it. We write out the results to another PubSub topic, and then we can go off and do whatever we need to do. Oh, no. Of course, let's take a look at the code now. So in the beginning, as mentioned, we have two topics, PubSub, reading from PubSub, topic A and topic B. I'll just keep doing this for a bit, sorry. We've keyed them, so you notice the keys here, key A and key B. We then flatten, merge the two pipelines together, and use a keyed model handler, as Sachin mentioned. This allows you to use the keys in subsequent transforms, so you can identify them from where they began. And then we just simply run the Gemma model, which is a lightweight, open LLM from Google. And then finally, we write it out to PubSub topic. I apologize for that. Hopefully, you'll agree that this is still fairly low code. And a lot of the typing that we did here is simply descriptive, where we're just trying to make it more readable, which is always nice in code. So let's actually go and run an example here. So normally in your actual pipelines, you'll have a source system, like a log or event generator or something that is pushing to PubSub. In our example, let's just write something straight from PubSub. And let's take a quick simple sentiment analysis. So it says, analyze the sentiment. I'm very excited today to present to everyone, but I'm also extremely nervous. We publish this. And when we go over to our subscription, the topic that we wrote to, we can pull this message in real time. And as you can see, let me do that. We just ran it, so the publish time is 1:52. You can check the timestamp. And the sentiment is mixed. While the person is excited to present, they're also feeling extremely nervous. And that's it. Thank you. And we're going to have Edgar from Spotify to tell you about how they use Dataflow ML.
Hello, my name is Edgar. I am a machine learning engineer in the personalization team at Spotify. Today, I'd like to talk about how Spotify has scaled machine learning podcast previews using Dataflow. But I wanted to start with a question here. Like, how many of you here listen to podcasts? Okay, quite a bit, good. Now, think about the most recent podcast that you listened to, and how did you discover it? Like, I imagine a lot of you are going to be thinking that maybe a friend of you or someone in your family recommended that podcast to you. The reality is, we used to rely a lot on our social connections for podcast discovery. And why is that? Podcasts have an opacity problem. So what does that mean? Like, how do you know that you're going to like a new show? Like, you see the title, you see the cover art, but you have to know the specific topic. You have to hear the host, feel the vibe, and understand the format of that podcast. And that's a lot of information, right? And what's the best way to get all of that information? It's by listening. But you can't listen to everything. There's just too many podcasts out there. How do you do it efficiently and effectively? That's why we built podcast previews. So we extracted these key moments in every episode and created these previews to allow you to easily get all of that information that you need to find out if you're like a new show or not. So today I wanted to talk about three things here. We're going to go through how we make previews for podcasts, but more importantly, what were the technical challenges that we had to overcome, and what were some of the lessons that we learned when running ML pipelines that you can take with you here. All right, to find these key moments in the episode and extract these 1-minute clips, we had to make sure that we were avoiding some uninteresting parts of the episode, like ads, maybe regions of silence or music. And we also had to make sure that the start of the previews was easy for you to follow. It had to be strong and it had to be catchy. So we had to avoid that the previews were just starting mid-sentence, right? Otherwise, you wouldn't be able to really follow it. So there was a lot of machine learning in content understanding work to be done here. Another challenge was the fact that some of our models, they were only trained on textual data in English. So we had to create a filter for episodes in English before sending those into our machine learning inference workflows. To do that, we had to train our own language identification model and run it at scale for every episode that went through our pipeline. Scalability was also another issue. Not only Spotify ingests hundreds of thousands of new episodes per day, but the podcast format itself, it's inherently long. Like an average podcast episode is about 40 minutes long. So we're talking here about a very large volume of audio and text data to be processed. And lastly, speed. So once an episode is ingested, we have to make sure that a preview is ready to be served within minutes and not hours. Okay, so how do we make all of this a reality? Let's take a look at the previews pipeline here. Once an episode is ingested, the first thing we have to do is identify its language. We have to make sure that only episodes in English go through our pipeline. If the episode is in English, then the next step is to download that episode in the form of audio, transcript, and those become the two main ingredients used to find the optimal offsets for our previews. Once we have these offsets, then it's just a matter of cutting the audio file and storing it in the form of audio and metadata. And I wanted to dig a little bit deeper into these two steps here, because that's where we're running machine learning inference at scale. So in this step, our task is to predict the language of an episode using its audio. So this pipeline is composed of 3 different workflows. The first one, it's an unsupervised speaker diarization, which basically segments an audio recording streaming, and then it uses clustering to identify the different speakers in each segment. We then produce embeddings for each one of the speakers using VGG-Vox, and then we use those embeddings to infer the language through a classifier. Now, the workflow that finds the optimal offsets for previews, it's a complex stack. So we're looking here at a very simplified diagram, but you can think of it as a collection of ML models, sort of like a mixture of experts where each model has its own specialty, right? So we have a model that classifies audio as either music or speech. We do sentiment analysis on different regions of the episode. We have to detect ads in the episode, and we also extract topics. And as you can imagine, running all of these models on long-form audio, it's very demanding in terms of not only memory, but also computing resources. Also, we had several iterations of this DAG. So to manage these different versions, we decided to package all of these models in our own Python library. That way, we use the same pipeline for both production and a testing environment, and the only difference between the two was really the version of our package. Now, the downside was that we had one very dense Pardue step where this entire collection of ML models was running. And in the end, that really compromised pipeline visibility for us. Okay, so now that we've covered how we make podcast previews, let's take a look at some of the challenges that we faced during this journey. In the first version of previews, our pipelines were all hourly batch. So at some point, we realized that many of the cards in the home feed, they didn't have a preview available, like this one in the example here. And why was that? Like, our pipeline wasn't broken, but it's just that it was taking too long to generate these previews. So once an episode was ingested, we realized that we had to create these previews within minutes and not hours. So what did we do? We converted our pipeline from batch to streaming. To do that, we use Spotify's open source framework Clio that does audio processing. And with that, we were able to reduce latency to generate the previews from 2 hours to 4 minutes. And from that, we learned two things. So conversion from batch to streaming is fairly easy. Like, if your DAG is not going to change, the code really doesn't change much from one to the other. But it's also a good idea to start with a batch pipeline before moving to streaming. And I say that because batch pipelines are usually easier to troubleshoot and manage. All right, another issue that comes up sometimes are hanging jobs. And by hanging here, I mean that the job simply never finishes. There's always a few workers there or one worker that just lingers there. And this can happen because of a bad actor in the input data. This bad actor might be causing errors like a download failure, or it's just getting stuck when running ML inference. And this can be very costly, especially if you're running a job with GPUs. Like, sometimes we just realized there was this job running for hours or even days, doing basically nothing, and we were just paying for it. So how do you mitigate this problem? Don't save all of your outputs at the end of your job. Like, save your outputs as elements are successfully processed. That way, even if some of the elements fail or your job gets stuck, you're not going to lose your entire job's work. You can add a timeout to your job as well. So for example, if you know that your workflow usually finishes within an hour, you can make it automatically stop if it takes longer than that. And as a safety net, it's also good to add alerts on the job lapse time here, because the timeout is not 100% reliable. Like, we still have a few cases where we get an alert and we have to manually go and cancel these jobs. Another challenge we had was managing dependencies. So there were a few factors that are important to call out here. We had many models like topic extraction, ad detection, audio classification, and so on. The models were trained on different frameworks like PyTorch, TensorFlow, and we were running all of them in the same Dataflow job. And the result of that was our project became very fragile, and we started seeing these build errors and runtime errors every now and then. So what did we learn here? Split your workflow into multiple workflows so that dependencies are much more manageable. Like, in our case, it would have been much better if we had a workflow just for ad detection, another one for sentiment analysis, and etc. Also use tools like Poetry and pipcompile to manage your dependencies. They don't solve all of the problems, but they sure make it a lot more easy to manage dependencies. And talk about dependencies. Our last challenge was a bit of a short story when we upgraded to the newest version of Apache Beam. So after upgrading, we start seeing this error like SDK harness disconnected. It's a bit cryptic. But this error usually indicates that the process running the pipeline code has crashed, and the root cause might just be buried in a stream of logs. So we suspected that it could be an out-of-memory issue because sometimes that's the error message we get. We ruled out that it wasn't because in the past we were able to process even larger batches than these ones. And after a lot of troubleshooting with the help of Google, we found out that there was a specific version of PubSub Lite that just wasn't working well with another version of the gRPC IO. And that was being caused by a transitive dependency coming from Apache Beam. Now, since we didn't use PubSub, the solution was just to uninstall PubSub Lite after all of the dependencies were installed in our Docker container. The main takeaways here were: be wary of transitive dependencies when upgrading Apache Beam, and also emulate your Dataflow runner environment. And you can do that with a GPU-equipped VM. That really helped us troubleshoot this problem. All right, and despite all of these challenges, we have successfully launched podcast previews. And using Dataflow as our platform to scale machine learning, we are able to ensure that more than 99% of the card impressions on the whole feed have an audio preview available. We also achieve very high throughput, so during peak times, right before launch, we were able to produce more than 8,000 previews per hour. And finally, we were able to keep up with the growth of the podcast catalog at Spotify. So at the moment, we have already run our language identification pipeline on more than 14 million episodes. As future work, we'd like to try out some of these latest features for ML inference on Dataflow, like Dataflow right fitting that would allow us to specify the right resources for each Dataflow step instead of having a single configuration for the entire pipeline. This would optimize resource allocation by dedicating less resources to simpler tasks like reading inputs and writing outputs. We're also excited about Run Inference API, which would not only increase throughput with its dynamic batching capability, but it would also allow us to break down our dense Purdue, the one where we run our collection of models, into smaller steps. Lastly, I'd like to thank my colleagues Diego and Winstead, who helped a lot in this presentation. They are also the co-authors of the blog post that originated this talk. All right, now to wrap things up, I'm going to pass it back to Sachin.
Thank you, Edgar. Thank you so much, Edgar. Really appreciate it. Just a couple of things, and then we'll have a little bit of time for Q&A. I wanted to highlight some third-party recognition for Dataflow that we've recently got. So Google is the only customer choice for stream processing, as announced by Gartner. So very excited, to see other customers, being successful with Dataflow and recommending it to others. And then, of course, Forrester also recognizes Google and Dataflow as a leader when it comes to streaming data platforms. Very excited about it. And again, the real-time AI, the real-time machine learning is a real critical key capability, one of many, of course, with Dataflow, but very, very proud of the work that we've done there. So, we've got you excited. Please do scan the QR code to get personalized guidance on Google, Cloud overall, Dataflow specifically, and some of the offers that we have. And we do value your feedback. Please do complete the session survey in the mobile app so we can make these sessions at next year's Next even more relevant to your interests.